All right, jumping into our next section. So differential equations. So a differential equation is an equation that describes the relationship between a function and its derivative. For example, dy dx equals negative x squared over y. So this is a differential equation, and a differential equation just pretty much, we're looking at we've got a function here and a derivative here. So this is describing a relationship here. And so that's the main point. So yeah. Now, let's move on to the next bit. So pretty much, a differential equation just relates the derivative to its function, and the function being of x, we're pretty much going to have, because we've got dy dx here, we've got y and x is here. Now, these can get more complex, so have a look through some of the ones in the text. They've got example ones. Now, a solution of a differential equation. A solution of a differential equation is a function y in terms of x which satisfies the differential equation. So if we were given dy dx equals 2xy, it has a solution of y equals e to the x squared. Or dy dx equals y squared has a solution y equals negative 1 on x. So when we're thinking about these, I'll just zoom in a little bit here. And I'll use the blue here. If we were thinking about y equals e to the x squared, if we were going to take the derivative of this, dy dx, we would have, well, it's going to be e to the x squared because an exponential, e to the x is, the derivative of e to the x is e to the x. And then we've got to do the derivative of the inside, which is 2x to the power of 1, so just doing a chain rule, which gives us the derivative of 2x e to the x squared. Now this here can be written as 2x, and then e to the x squared was y. That was our function. So that's why in this particular example, 2xy, the derivative of 2xy has a solution y e to the x squared. Now let's go down the general solution. So while we had dy dx equals 2xy, and it has the solution y equals e to the x squared, it could also have the solution y equals 2e to the x squared, because if you think about it up here, if I do this chain rule again, I'm just going to have that value out the front, and it's still going to be able to sub in y. So considering these two solutions, 2 to the e x squared and negative 7e to the x squared, we can write a general solution here, which is y equals some constant e to the x squared. All right, so almost finished the definition. So if initial conditions are given, then we can evaluate for C and solve for a particular solution. So we'll see that in our example question. So let's jump down to our example question now. So we've got, consider the differential equation dy dx minus 3y equals 3. Show that y equals ce to the power of 3x minus 1 is a solution for the differential equation for any constant c. So let's do our first step here. Let's do our derivative. So let's change back to pen. So we're going to do dy dx here. And this equals ce to the 3x. And then we've got a chain rule in here. So we're going to have, this will just become 3 there. All right, so ce to 3x, and then minus 0, because the derivative of that is 0. So we've found the derivative here equals, I'll just rewrite it, 3ce to the 3x. And so now we're showing that it's a solution for our differential equation we were given above. So our differential equation was dy dx minus 3y equals 3. So I'm just going to leave it like that, dy dx minus 3y. So let's do dy dx. So dy dx was 3c e to the negative e to the 3x. And then we've got minus 3, and our y equation for this particular one was c e to the 3x minus 1, okay, which this thing here is going to be 3ce to the 3x minus 3ce to the 3x negative 3 times negative 1 gives us plus 3. Okay, these two values cancel out. And so we've got equals 3, which was the solution up here to our differential equation. So this is correct. So we've got, therefore, the differential equation, so our differential equation at the top, equation is satisfied for all x real numbers for any constant. So this is a little bit over, this is just a very specific, but it's pretty much saying that like whatever x value we have, it's not going to matter, and whatever for any constant here, because the constant is going to be the same in this function and in the derivative function, they're going to cancel out, and we're left with that. Now, the next bit it says, next bit of the example, it says sketch the solution for the curves for c equals 0, plus or minus 1, plus or minus 2, plus or minus 3. So if this equals 0, when you think about our function here, we're going to have negative 1. So let's do this one first. So this one's the easiest because it's straight over this way. So this would be c equals 0. Now, the next one's a little bit harder, and what I would consider doing is, I'm just going to draw with the pen. So you got to remember that this, our solution function here is an exponential. So e to the 0 would give us 1. Remember when we practice graphing these, they go like this through 1. Now the negative 1 means we've got sort of we're translated down by 1. So this would be like that origin. We're going to go through this origin value. So let's consider the plus or minus 1 here. So maybe I'll do them in this color here. So plus or minus 1, I'm going to see this value here would be c equals 1. So we would have e to the 0 gives us 1. So we're going to have 1 minus 1 is going to give 0, or negative 1 minus 1 gives us 2. So those are the two values there. It's going to start there and it's going to curve out. And I'm shocking at drawing graphs. So c equals 1, and this is going to be c equals negative 1. And let's do green for our plus or minus 2. Now, if we think about this value up here, if this equals 2, we're going to have 2 minus 1, so it's going to go through 1. Or it's going to go through negative 3, because it'll be negative 2 minus 1, which is negative 3. And these just come through this way. And to be honest, I would be using my graphics calculator, using the trace mode for these, but this is c equals 2 and c equals negative 2. So let's keep tracking on. So find the particular solution which passes through 0 and 2. So in this particular case, we can we're looking at our y function. So we were given y equals ce to the 3x minus 1. And it goes through 0 and 2. So if it goes through 0 and 2, it means when x equals 0, y equals 2. So we're going to have 2 equals ce to the 3 times 0 minus 1. So let's add 1 to both sides. We're going to have 3 equals c e to the power of 0, which therefore means c equals 3, which is easy. So we've got that there. So c equals 3. Therefore, now this is where we're looking at a particular solution. Therefore, the particular, yep.
Do you mark the test yet?
The particular solution is going to be y equals 3 because we picked 3e to 3x minus 1. So we've got that particular solution there. All right, so we've got that in this. That's our particular solution for when we're given a scenario. So this is like our initial conditions in this one, and this is part of what this definition up here was saying. If initial conditions are given, then we can evaluate for C and solve for that particular solution. Now the last bit, find the equation of the tangent to the particular solution at 0, 2. So you got to consider here dy dx, if we remember, was given by I'm just going to erase that because we weren't given dy dx, we were given dy dx minus 3y equals 3, which therefore dy dx equals 3 plus 3y. So I'm just going to do that for this particular one, because this means that for this particular one here, we can go, well, we're looking for dy dx at 0, 2. So we're looking for slope of tangent at 0, and we're looking for that particular solution. So that means that here we're looking at, well, y is 2. So if y equals 2, we're looking at this equals 3 plus 3 times 2, which gives us 3 plus 6, which equals 9. So we're looking for, we've got our gradient here because it's dy dx. So we've got a gradient of 9, and we've just got to figure out the equation of the tangent. Now I'm going to use a slightly different equation here. In this particular one, we've previously done y2, the slope equals y2 over y minus y1 over x2 minus x1. Now this is the rise over run formula. Now in this particular one, we are given that 9 is our slope. Now for this particular one, y2, x2, I'm just going to use the coordinate x and y. So I'm going to use the variables there. And then, so I'm just going to go this would be x2 and y2. And then I'm going to use these ones as x1, y1. Because in this space, this means that I can go, well, this is just going to be y minus 2 over x minus 0. Therefore, we can quickly rearrange this. We multiply x by both sides, and then we add y, then we add 2, sorry. We're going to get y equals 9x plus 2. And that's the equation of the tangent. Now, we would check this in our graphics calculator, and when we would check this, we would check it with graph of y equals 9x squared, and we would be doing y equals 3e to the 3x minus 1, and this should intersect, and it should only intersect once at 0 and 2. Thanks, that's it for that one.